OSPF DR and BDR. In this video, I am going to talk about two concepts related to some type of OSPF network. The first is DR and the second is BDR. You have heard about the DR and BDR in this video, in previous videos, but here we will talk about the detail of the DR and BDR. And after that, you can see that we need to know about DR, BDR for understanding other features, for example, other features related to the link states, some type of link states, and also some other things. Let me to talk about the OSPF DR and also OSPF BDR. What is the DR? DR is the abbreviation of the designated router, and BDR is the abbreviation of the backup designated router. Okay, actually DR is a role for one interface and BDR is another role for one interface when you have OSPF configured and on some type of interfaces. Here, as you can see, we have four routers, R1, R2, R3, and R4. They are connected to one multi-access network. Here we have multi-access network, not a point-to-point network. Okay, this is a broadcast multi-access. In broadcast multi-access network, okay, as you can see, we can send broadcast from R1, and this broadcast can receive by R2, R3, and R4. And also we can send multicast packet such as the OSPF hello packet. This OSPF packet can be reached to R2, R3, and R4. You know that in previous video we have learned about the non-broadcast multi-access or NBMA. This is the broadcast multi-access or for example BMA. Okay, let me to talk about the broadcast multi-access network such as the Ethernet network. As you can see here, we have four routers, and you know that when we are configuring the OSPF on these routers, one IP address, one multicast IP address automatically will enable on all of the interfaces with OSPF. For example, here we will have the multicast address of the 224.0.0.5. Why? Because we have configured OSPF on this interface and also on this interface, and also on the router 3's interface, and finally on the router 4 interface. After that, you know that the R1 is sending its hello to the 224.0.0.5, and this hello can be received by the router 3, okay, and also the router 2, and finally with the router 4. Okay, what does it mean? It means that the R1, okay, sends its hellos with one packet, with one multicast packet to all routers connecting to this broadcast multi-access network, to this Ethernet network. Also, after the R1, the R2 should send its multicast packets. Again, the R2's hello can receive with the R1, R2, R3, and R4. And also the R3 should send its hello packet, R4 should send its hello packet. And finally, we will have neighborship between all routers. Let me to write here, we will have neighborship between the router 1 and router 2, then router 1 and router 3, after that router 1 and router 4, then router 2 and router 3, router 2 and router 4, and finally router 4 and the router 3 and the router 4. Okay, as you can see here, in this simple scenario with only 6 routers, okay, 4 routers, we will have 6 OSPF neighborship. If you want to find the number of neighborships in each broadcast multi-access network, you can use this formula: n multiply n minus 1, okay, divided to 2. N is the number of the routers. For example, if you have 4 routers, you can use easily the number of neighborship. 4 multiply 3 divided to 2 equal to 6. Assume that we have 5 routers. Okay, if you have 5 routers, you will have 5 multiply 4, okay, divided to 2. This is equal to 10. And let me to for example increase the router number to 6, and then we will have 6 multiply 5 divided to 2, 15. If you use, for example, if you have 10 routers in the multi-access network, this is a result to 10 multiply 9 over 2. This is equal to 45. As you can see, the neighborships numbers are increasing when we have more than, for example, 3, 4, 5, or a little more routers. And as you can see, when you have a 10 router or more, you will have many neighborships. Okay, this is the first thing that in this picture you can see. Look at here. Here we have 4 routers and we have 6 neighborship. Assume that we have, for example, a 10 router, you will have 45 neighborship. Okay, after that, you know that each neighbor should send its link states to other routers. For example, assume that R1, okay, has one link state of R1. You know that the R1 should send its link state to router 2, to router 3, to router 4. Why? Because we have neighborship with all of these 4 routers. Also, the R2 should check the link state of R1, availability of link state of R1 in R3 and R4. Also, R2 should check, R4 should check. Then R2 should send its link state to other routers. R3 should send its link state to other routers. R4 should send its link state to other routers. And this means that we will have many, for example, packet exchange in the broadcast networks. And this is not so efficient. Actually, with this behavior, okay, with many adjacencies per segment, okay, we will consume more bandwidth, more CPU processing, and also more memory to maintain each of the neighbor state and also the link state exchange. OSPF overcomes this inefficiency by creating a pseudo node, okay, that is a virtual router to manage the adjacency state with all other routers on that broadcast network segment. Let me to talk about it. Look at here. You know that in this network, actually, physically, we have only 4 routers. Now, assume that here in this network, we are using one of the routers as the DR. I will talk about the pseudo node, but before pseudo node, let me to say that here, assume that we have one router as the manager of the network. Assume that the router 1 is the manager. We call the manager the DR router. Okay, let me to write here. DR is the designated router. What is the benefits of the DR? The benefits of the DR is that all of the routers, okay, only should send their updates to the DR. In the DR, we will have one special multicast IP address, the 224.0.0.6. Okay, this IP address, this multicast IP address, should enable on DR automatically. Okay, and all routers, for example, router 2, router, for example, 3, and router 4. When want to sending their update, they should send their update to this 224.0.0.6. For example, router 2, this is the router 2 link state of R2 is sending from the R2 to the router 1 with one packet, okay? And you know that the destination IP address of this packet is 224.0.0.6, not 224.0.0.5. Why? Because we want to send this update only to the DR. This IP address only is available on the DR. After that, the DR, okay, should send this update, okay, this update received from the this link state received from the router 2 with another update link. This is the link state of R2 to all other routers, for example, to the 224.0.0.5. You know that this IP address now is available on the router 2, router 3, and router 4. Because of that, this packet is receiving to router 2, router 3, and router 4. Router 2 should discard it, router 3 should accept it, router 4 should accept it. Actually, we are sending everything to the router 1, to the DR, and DR is propagating this information to other routers. Assume that R1, without the DR, concept of DR, we should send everything ourselves to other routers. But here we are sending only to DR. This is the manager of the link state propagation, and the DR should send the information to other routers. This is more efficient. Okay, and also R3 should send its link state to DR, and DR should send to other routers. Again, R4 should create its link state, send to the DR. DR should propagate to other routers. Okay, this is a more efficient behavior than the default behavior that I have explained it. Okay, here you don't need to talk with all routers, only you need to talk with the DR, and DR can send information to the other routers. Assume that with this behavior, okay, we have one DR. And also let me to say that another router here also is available, such as the for example router 4. This is the BDR. BDR means backup DR. On the BDR also we have the same multicast IPv6 address, IPv4 address 224.0.0.6, but you know that BDR is the backup of DR, means when the DR is available we don't use BDR. Actually, the router 2, when sending its link state to the destination of 224.0.0.6, this update can be received with the router 1 as the DR, and also with the router 4. But the router 4 doesn't do anything. Only it should, for example, receive the packet, the update, and if the DR fail, the BDR can use as a new DR, and after that it can send information to other routers. But when the DR is available, the BDR only is hearing the updates, and this is the DR that send the update to the other routers. This is the functionality of the DR and also BDR. DR is the active router, and the BDR is a standby router for replacing the DR. Also, in some cases, okay, actually we can imagine that we have a virtual router. Assume that here, you know that here in the physical network, 4 routers, router 1, router 2, router 4. But let me to show you one virtual router. This is not real. This is only our imagination. This is a virtual router. Okay, here we have this virtual router, and actually this is the router 1. You can imagine that this is the router 1 here. Okay, and after that, because of that, we call it pseudo node. Okay, this is not physical node, this is the pseudo node. Why? Because you know that actually all of the routers only should talk with the router 1, and this is the router 1. Actually the router 2 doesn't connect in for example logic with to the router 3 and to the router 4. All of them are connecting to this virtual router. Okay, you know that the router 2 send its updates to the router 1, or the router 3 again to router 1, also the router 4 to the router 1 as the DR. Because of that, all of them are talking with the DR actually. Okay, this is the DR. You can imagine this DR is here, and because of that, actually we are converting this physical network to this logical network. Okay, you will learn more than this about the pseudo node when I'm talking about the link states and the different types of the link state in the OSPF. But here you can see these 4 routers. Okay, network now is converting to this network. We have again the 4 routers, but this is a pseudo node, and this pseudo node actually is the DR. Okay, maybe you ask me how the DR is selecting. Let me to talk about it, because it is important for us. In the OSPF, in broadcast network, for one interface we have one criteria. We call it OSPF priority. Okay, for each of these interfaces we have one OSPF priority. For example, for the interface of router 2, for the interface of router 1, for the interface of for example router 4, and also for the interface of router 3, we have OSPF priority. The default value of the OSPF priority is 1. Okay, also here the default value is 1, and also here the default value is 1, and also in the router 3 the default value is 1. You can change this default value with this command. Look at here, router config. Okay, we should go to the interface mode, interface, then interface name, router config if. Now you can configure IP OSPF priority, then the value of the priority. Okay, after configuring the priority, now we can talk about the mechanism of selecting DR and BDR. The DR is the router with the highest interface priority. Actually, it is the interface with the highest OSPF priority. DR is the highest OSPF priority. Don't forget that In some cases, we have, for example, all interfaces without without any difference about the priority. All of them are using the priority one. If the priority is equal, the next we have a tiebreaker. Highest router ID, highest OSPF router ID. Okay, the highest OSPF router ID is selecting the DR. Actually, for example, in the router 1, we have priority 1, in the router 2 priority 1, in the router 3 priority 1, in the router 4 priority 1 on this interface. And now the router ID is the selector, or is the mechanism that we are using it for the selecting the, for example, DR. The next highest priority or the next highest OSPF router ID is the BDR. Okay, let me to talk about this, but let me to say that if you configure one router with the priority of 0, this means that you don't want to use this router as the DR or BDR. For example, assume that I am configuring the router 3 with the priority of 0. What does it mean? It means that this router cannot be selected as the DR and also BDR. Okay. And after that, here in this scenario, I'm going to configure the router 1 as DR and the router 2 as and also, for example, the router 4 as BDR. But before configuration, let me to say that if you configure OSPF on all of these interfaces without configuring the priority, the OSPF automatically, okay, should select the DR and BDR with the highest OSPF router ID. Okay, because of that, when we are working on the Ethernet network, on the broadcast networks like this network, okay, you will see that after 40 seconds, we call it the wait time, the equal value of the wait time. The value of a wait time is equal to the dead time, and the value of the wait time is 40 seconds. After 40 seconds, the selecting of DR and BDR completed, because we need to wait for other interfaces to be configured. Okay, let me to show you. You will learn all of this in this video. Look at here. R1 first. We should configure the interface fast Ethernet 00 with the IP address of the 10.0.0.1, then 255.255, okay, 2550, that's it, and then no shutdown. Let me to configure also the router 2. This is the router 2 conft interface fast Ethernet 00, IP address is 10.0.0.2, 255.255.255.0, and then no shutdown. After that, the router 3 conft interface fast Ethernet 00, IP address is 10.0.0.3, 255.255.255.0, and then no shutdown. And finally, the router 4 conft interface fast Ethernet 00, IP address is 10.0.0.4, 255.255.255.0, and then no shutdown. Now we have connectivity between the router 1, router 2, router 3, and 4. Let me to show you ping. For example, 10.0.0.2 from the router 1. We should wait some second. Okay, ping 10.0.0.3. And after that, we can try to check the connectivity with the 10.0.0.4. That's it. Now, let me to configure OSPF on all of these routers. For example, in the R1, okay, on the interface fast Ethernet 00, I'm going to configure IP OSPF 1 area 0. That's it. Okay. After this configuration, if you check do show IP OSPF interface fast Ethernet 00, you can see that we are waiting. Wait time before designated router selection, and we should wait about 40 seconds. As you can see, 35 seconds is remaining. Let me to configure the router 2 IP OSPF 1 area 0. Then router 3, as you can see, the neighborship doesn't establish. After that, IP OSPF 1 area 0 in the router 3, and also in the router 4, IP OSPF 1 area 0. We should wait about 40 seconds. And after that, let me to say that in broadcast networks, we have one DR, one BDR. Other routers has another role. We call it DR other. DR other means no DR and no BDR. Okay. For example, in one broadcast network with 4 routers, we will have one DR, one BDR, 2 DR other. If you have 10 routers, you will have one DR, one BDR, and then, for example, 8 DR others. And now let me to show you what is happening. As you can see, again, we should wait, because after 40 seconds, we are selecting the DR and BDR. As you can see now, the DR and BDR is selecting. Here you can see the log of neighborship. What is occurring? Let me to show you what what's happened. Let me to say that when you are using the broadcast network or multi-access network and the DR and BDR selection is occurring in this network, you know that we will have one DR, one BDR, and also multiple DR others. Okay, about the adjacency, all of the routers are adjacent with each other or are neighbors with each other, but only they are reaching to the fully adjacent with the DR and BDR. For example, here the router, the DR other router, you know that DR other router is like the router 3 and router 2. Okay, I will show you DR others can reach with each other to the two-way state. What does it mean? They are neighbors, but they don't exchange the routing information with each other. Okay, but they are neighbor. DR other with the DR, okay, can reach to the full state. Why? Because you know that they should exchange the information or link state with each other, and also DR other with the BDR can reach to the full state, and after that BDR with the DR, okay, can reach again to the full state. I will show you. First, let me to verify the status of our scenario. You know that I didn't configure Ospf Priority. We expect that the highest router ID is selecting as the DR, and because the highest router ID is the router ID of router 4 10004, the router 4 we expect that now is selecting as the DR, and also the router 3 we expect that should be BDR. Let me to check it from the R1. We can start. This is the R1. You can use show IP OSPF interface fast Ethernet 00, this interface. Okay, here you can see about the show IP OSPF interface fast Ethernet 00. The state of this interface is DR other. It is okay, and the priority of this interface is 1. It is okay. Okay, in the router 2. In the router 2, again, we will see the same condition, show IP OSPF interface fast Ethernet 00. As you can see, the router 2's interface is the DR and priority is 1. OSPF priority is 1. Okay. The router 3, this is the router 3. Let me to show you. Show IP OSPF interface fast Ethernet 00 can show us the router 3's interface state is BDR and the priority of this interface is 1. It's okay. Then in the router 4, let me to show you. This is the DR. Show IP OSPF interface fast Ethernet 00. As you can see, the router 4, okay, the router 4's interface, actually this is not the router, this is the interface state. Interface state now is the, for example, DR. Okay, and after that, about the interface fast Ethernet 00, the state is DR and priority is 1. Because you know that the priority is same and we need to use the highest router ID, okay, as the tiebreaker. Also, let me to show you the status of R1 now. R1 interface, show IP OSPF interface fast Ethernet 00. On this interface, as you can see now, show IP interface fast Ethernet 00, it is better. Here you can see we have only one multicast IP address, 224.0.0.5. On the router 1, okay, and also on the router 2 we have again only this IP address, show IP interface fast Ethernet 00. As you can see, we have 224.0.0.5. In the router 3, let me to show you, show IP interface fast Ethernet 00. We have two IP addresses, 224.0.0.5 and 224.0.0.6. Why? Because this is BDR. And also in the router 4, let me to show you, show IP interface fast Ethernet 00. As you can see, show IP interface fast Ethernet 00. We have again two IP addresses. Why? Because this is the DR. Okay, how we can change the DR and BDR? Look at here. The DR and BDR election is not preemptive. What does it mean? It means that if you increase the priority of router 1 from 1 to 100, okay, the DR and BDR election doesn't change, because when we are selecting the DR and BDR, until the DR is available, we will not have any new DR, or we will not have any BDR. If the DR fail, the BDR will be the new DR. Okay, if the BDR fail, we will select the new BDR. Okay, let me to show you. On the router 1, this is the router 1. I'm going to configuring the priority as 100, interface fast Ethernet 00, IP OSPF priority. For example, you can configure priority between 0 to 255, 100. Now we have higher priority on the interface of the router 1, but show IP OSPF interface fast Ethernet 00 can show us that a state is again DRother and the priority of this interface is 100. Why? Because you know that the DR and BDR election is non-preemptive process. Also, in the router 2, let me to configure the priority or OSPF priority as the, for example, 50. Because I'm going to configuring these two routers as a DR and BDR. Let me to go to the router 2's interface. Here conf-t interface fast Ethernet 00, IP OSPF priority is, for example, 50. Again, we don't have any change. Show IP OSPF interface fast Ethernet 00 can show us that the priority of this interface is 50 and the state is DRother. Why? Because we have DR and BDR. And also in the router 3 and router 4, let me to change the priority of these two interfaces to 0. Or if you want, you can clear IP OSPF process, but it's better to configuring the priority as 0. IP OSPF priority 0 in the router 3 and also in the router 4 conf-t interface fast Ethernet 00, IP OSPF priority 0. That's it. This is our configuration, and now we have the priority of 0 on this interface and the priority of 0 on this interface. And finally, now the router 1 is our new DR router because of its highest priority, and the router 2 is our new BDR router because its next higher priority. Router 4's interface is DRother and router 5's interface is DRother again. Let me to show you. Starting from the router 1, show IP OSPF interface fast Ethernet 00 can show us that the interface of router 1 now is DR and the priority of this interface is 100. In the router 2, show IP OSPF interface fast Ethernet 00 can show us that the interface of router 2's state is BDR and the priority of this interface is 50. It's okay. In the router 3, do show IP OSPF. Okay, do show IP OSPF interface fast Ethernet 00 can show us that the state of this interface is DRother and the priority is 0. It's okay. And then in the router 4, do show IP OSPF interface fast Ethernet 00 can show us that the priority of this interface is 0 and the state is DRother. Also, in the, for example, let me to show you the result of show IP OSPF interface brief. Here you can see that the state of the interface of router 1 is DR, it is okay. And also the state of interface of router 2, show IP OSPF interface brief, you can see the state is BDR, it's okay. And also in the router 3, show IP OSPF interface brief can show us that the state of the interface of router 3 fast Ethernet 00 is the DRother. And also in the router 4, we have the similar condition. Show IP OSPF interface brief. As you can see, the state of fast Ethernet 00 is DRother. Okay. Also here we can use the show IP OSPF neighbor. Show IP OSPF neighbor can show us in the router 1, this is router 1, router 1 is the DR. We have 3 neighbor. Router 2, this is the router ID of router 2, this is the router ID of router 3, and this is the router ID of router 4. As you can see, the priority of interface of router 2 is 50, the priority of router 3 is 0, the priority of router 4 is 0. Because the router 1 is DR, okay, we have full adjacency, okay, with these 3 routers, with the DRother and also with the BDRs. Look at BDR and DRothers, DRother, BDR. Now we can understand these fields: neighbor ID, priority, state, date, time, address, and also interface. Everything in the neighborship table. Let me to show you the show IP OSPF neighbor in the router 2. Show IP OSPF neighbor in the router 2. This router can show us that we have 3 neighbors: router 1, router 3, router 4. Don't forget that the router 2 is the BDR and the priority of router 1 is 100. This interface, the interface of router 1, and the priority of the interfaces of the router 3 and 4 are 0. Then we have again full adjacency with all routers, with DR and with the DRothers. Let me to go to the router 3. Router 3 is the DRother, show IP OSPF neighbor. Can show us that we have again 3 neighbor, router 1, router 2, and router 4. The priority of router 1 is 100. The priority of router 2 is 50. The priority of router 4 is 0. We have full adjacency with DR. We have full adjacency with BDR. But with the DRother, we have only two-way neighborship. Now you can easily understand these terms. Let me to go to router 4. Show IP, okay, show IP OSPF neighbor. As you can see, again, here we have 3 neighbor, router 1, router 2, router 3. Router 1's interface priority is 100, router 2's interface priority is 50, router 3's interface priority is 0. We have full adjacency with DR, we have full adjacency with BDR, but we have two-way adjacency with the DRother. We can easily understand these terms. Now, let me to show you again, show IP OSPF interface brief. Look at here. We can understand everything in this show command. We have the OSPF on the facet and 00, process ID is 1, area is 0. This is the IP address of the interface of R1. The cost of interface is 1 because this is facet Ethernet. The state of this interface is DR. But here we have one new information. Look at here. Neighbors means the number of neighbors, okay, the count of neighbors. F is the abbreviation of the full adjacency, means we have full adjacency with 3 neighbors. Yes, it's okay, because in router 1 we have 3 routers as the full adjacent neighbor. Router 2, router 3, and router 4, you know that the router 1 is the DR. But here you have another for example character C. C means count of neighbors, okay, count of two-way neighbors or neighbors. Also we have 3 neighbors, 3 full adjacency neighbor, 3 neighbors. In the router 2, again, we have similar condition. Show IP OSPF interface brief. Look at here, 3 neighbors, 3 is the count of our 3 fully adjacent neighbor and 3 neighbors. In the router 3, it is interesting. Show IP OSPF interface brief. We have 2 full adjacent neighbor, DR and BDR, but 3 neighbor, 3 two-way neighbor. In the router 3, you know that we have 3 neighbor, 2 of them are fully adjacent neighbor. And then in the router 4, we have similar results. Show IP OSPF interface brief. We have 2 neighbor, 2 fully neighbor, okay, fully adjacent neighbor, and 3 neighbor count or 3 two-way neighbor. Also, in the router 1, I'm going to use show IP OSPF interface facet and 00. You know that the router 1's interface is DR. The priority of this interface is 100. Here you can see that designated router ID is 10001. Interface IP address is 10001. This is the router ID of the DR. This is the IP of the interface of DR, okay? Backup designated router ID means BDR ID is 10002. This is the IP address. Okay, and after that, here you can see we have neighbor count is 3, adjacent neighbor count is 3, means fully adjacent. Okay, adjacent with router 2, with router 3 and router 4, and router 2 is the backup designated router. In the router 2, show IP OSPF interface facet Ethernet 00. As you can see here again, we the state of this interface in the router 2 is BDR. The priority is 50. And also, as you can see, the DR ID is 10001, BDR ID is 10002, the DR interface IP address is 10001, and the BDR interface IP address is 10002. Also, again, we have 3 neighbor count, we have 3 fully neighbor count or fully adjacency. Then adjacency with neighbor 10001, this is DR, and also with the 10003 and 10004, the 2 DR others. In the router 3, show IP OSPF interface facet and 00. Look at here. The state of this interface is DRother, priority is 0. This is the DR router ID, this is the BDR router ID, this is the DR IP, and this is the BDR IP. Here you can see we have 3 neighbor count, and 2 of them are the fully neighborship, okay? Adjacent with 10001, adjacent with 10002. 10001 is the DR, and the 10002 is the BDR. Okay, and as you know, now we can use this, for example, virtual router for a more efficient exchange of information in the broadcast networks. You know that we don't have this concept on the point-to-point networks. Look at here. Assume that here I'm going to add one serial link to the router 1. First, we should save the configuration of these routers R1, and then in the router 2, let me to save it. Okay, after that, let me to stop the router 1. Okay, and also router 2 stop. Let me to add one serial interface to these two routers. This is the serial interface of router 1, and this is the serial interface of router 2. Okay, now let me to start these two routers, and then we can add one new interface to the router 1 and to the router 2, serial 10 to the serial 10. Okay, I'm going to show you what is happening when we are using one point-to-point network. You know that the concept of DR BDR is working only on broadcast network, not on the point-to-point networks. Okay, here we have serial 10 in the router 1 and router 2. If you want, you can use, for example, this range of IP address 10.120/24 is the range of IP address that I'm going to use between these two routers. Okay, this is our CLI. Let me to configure these two routers. R1 starting from the router 1, conft, then interface serial 10. IP address of this interface is 10.121.255, then 255.255.0, no shutdown, IP OSPF 1 area 0. And after that, on the router 2, conft, interface serial 10. Let me to show you interface serial 10. IP address is 10.122.255.255.255.0, no shutdown, IP OSPF 1 area 0. Now we will have one neighborship over the R1 over the serial 10 of the router 1 and router 2. Let me to show you. Show IP OSPF neighbor. As you can see, now we have another neighborship with the router 2 over the serial 10. And here with the priority of router 2 is 0, because in the point-to-point at all we don't have the concept of priority, and the state is full. Yes, every time in point-to-point networks we are reaching to the state of full. And also, as you can see, we don't have the concept of DR BDR or DRother. Because of that, it is important to say that this concept only is available on the broadcast networks, on the broadcast multi-access networks. This is a little beyond the scope of this time of class, but let me to say that in some cases, for example, in non-broadcast multi-access networks such as the frame lane network, we will have the concept of DR BDR. You can compare only two networks now, point-to-point and broadcast multi-access. Okay, in Ethernet network, as one of the broadcast multi-access networks, we have the concept of DR and BDR, but in the point-to-point networks, we don't have this concept. In this picture, you can see the functionality of DR and BDR. As you can see, we have 5 routers in step 1, and 3 of these routers are DRother, and 1 is BDR, and another is DR. Okay, we are sending the updates, the link state from the DRother to the DR and also BDR. Only the DR, okay, should acknowledge to the DRother, and after that, as you can see, the DR, okay, is sending these updates to the other routers. Let me to show you here. First, let me to remove the serial link, because I'm not going to talk about the serial links now. In the R1, we can shut down the interface serial 10 with the, for example, shutdown command, and also in the router 2, interface serial 10 shutdown. Okay, interface serial 10 shutdown. That's it. Now we don't have this link at all. And let me to configure one, for example, loopback 0 interface on the router 4. Router 4 is the one of the DRothers, quad 4/32 is the IP address of the loopback 0 of the router 4. And then I'm going to capture the link, this link, for example. I'm going to show you what is happening when we are creating one change in the OSPF. In the router 4, this is the router 4, we can configure this loopback interface, conf d interface loopback 0, IP address is quad 4, okay, quad 255. Then I'm going to enable OSPF on this interface. This is the OSPF hello. Look at here, we are using IP OSPF 1 area, for example, 0. As you can see here, now we will have one new update. This new update received from the router 4 from the 10.0.0.4 to the destination of 224.0.0.6, means DR and BDR. After that, as you can see, we are receiving the link state update from the 10.0.0.1, means the DR, to the 224.0.0.5. And after that, all routers, exclude the router 4, should send the acknowledgement. As you can see here, the acknowledgement of the router 3, okay, is sending to the 224.0.0.6, and the acknowledgement of the router 2 is sending to the 224.0.0.5. Means the here BDR is sending its acknowledgement to the 224.0.0.5, all OSPF router IP address, okay, and also the DRother is sending to the DR and BDR. That's it, okay. Here we didn't see the link state acknowledgement from the router DR to the router 4, but normally we should see it. Maybe this is related to implementation in one or in some of the IOSs. Also, let me to review the content of the hello packet when we have DR and BDR. Look at here, now you can easily understand all of the content of one OSPF hello packet, because now you learned about the OSPF DR and BDR election. Look at here, in the OSPF packet we have, in the OSPF hello, we have OSPF header. As you can see, the version is 2. You know that we are using version 2. And after that, the message type is hello. The packet length is 56 bytes. The source router ID is 10.0.0.1. This is the router ID. Area ID is quad 0 backbone router. Checksum is for example, verifying that this packet is noise free. Authentication type is null. Authentication data is there, for example, this data. We don't have authentication data because we didn't enable the authentication. You have learned about all of these concepts. And then in the hello packet, we have network mask, we have hello interval, we have router priority. Now you can understand the priority, router dead interval, designated router, backup designated routers, and also the active neighbors. Now you can easily understand all of these information. Also in future, in other courses, you will learn about the some of these options, some of these flags, and some other features that are available in the OSPF packets. Before finishing this video, let me to show you in the next time the states between two routers in OSPF. You know that in between the router 1 and 2, we are starting from the down state, then initialize state, then two-way state. Here, as you can see, we have DR election, okay? DR election dependent on network type. What does it mean? It means that if you are using point-to-point network type, means point-to-point interface, we don't have DR election. But if you are using the broadcast network type, okay, means Ethernet, for example, we need to use this step, DR election. And now you can easily understand everything in the for example, link state exchange and the states in the between two routers. Don't forget that when two routers are for example DRother, actually they are reach only to two-way state until here, okay? But when two routers are reaching to the full state, actually they are reaching to here, okay? Because of that, now we can better understand the difference between the between this simple neighborship, means two-way, and also fully adjacency. In fully adjacency, actually we have for example everything. We have neighborship, and also we have fully synchronized database between two routers. But in neighborship, we are only receiving the hello from the neighbor, and then hello is compatible with our hello. Because of that, we will neighbor. That's it, okay? And maybe we use in future about this for example this neighborship for other features. But for now, the two-way means nothing, okay? Maybe this means only we have one for example one simple conversation and with other routers, okay? But if you want to send information from one router to another router, it is mandatory to reaching to the full adjacency. All right, in this video we have learned about the OSPF DR and BDR election, and also about the OSPF states. Now we know everything, okay? In the next video, I am going to talk about a little more related to the, for example, link states, and also the different type of link state. This is so important for us for learning about the different link state advertisement in the OSPF. Actually, after learning about the neighborship, okay, and also the states and DR and BDR and some other things. It's time of talking about the link state database, and also the information are available in the link state database, such as the link state advertisement, different types of link state advertisement, LSA type 1, type 2, and some other things. This is so useful for us because we need to learn about these features for future configuration, for future advanced features that we have in the OSPF. Because of that, now you can review all of the concepts related to the OSPF until now. After that, please come with me to the next video. I will talk about the one of the most advanced topics in the OSPF. We call it link state advertisement types.